So now we are going to talk about the aliphatic hydrocarbon alkanes. So we know that alkanes from a homologous series with the general formula Cn is 2 n plus 2, where n is the number of carbon atoms in the molecule. The first member of the family has the molecular formula CH4, because here n is equal to 1, so carbon 1 and the hydrogen will be 2 plus 2, that means 4, so cs4 is the first member of the family of alkanes. So it is commonly known as methane, and the second member with molecular formula C2H6 is called ethane, and thus there is also methane, ethane, propane, butane. The carbon increases, the name, the changes of the alkane. And this we see that also these compounds are also known as saturated hydrocarbons, because in these hydrocarbons are relatively unreactive under ordinary laboratory condition. So because the carbon and carbon single bonded, which is sigma bond, the sigma bond is really strong. It is not intend to react with others molecules, so that's why it's remain unreacted in the some reaction. So that's why we called the alkene is the paraffins. The Latin param affins is the common word from the that's why the form of paraffins is called is means there's a little activity, so its activity is real little, that's why we call this paraffin. And now the classification of carbon and hydrogen atoms. So the primary carbons, we know the is also called the 1 degree carbon attached to one other carbon atom. So here you see that this carbon attached to it just one carbon atom, that's why it's called the 1 degree hydrocarbon. And 1 degree primary carbons, then the 2 degree or secondary attached with two carbons, and thus the 3 degree attached with 3 carbon, and the 4 degree attached with 4 carbons. And thus the classifications of carbon and hydrogen atoms: the primary, secondary, tertiary, and quaternary. So the is also there has primary hydrogens or secondary hydrogens and tertiary hydrogens. Primary hydrogens means the are attached to carbon bonded to one other carbon atoms. So attached to carbon is bonded to one other carbon atoms. So you see that in this hydrogen is attached to this carbon, and this carbon is only attached to the one carbon. That's why we call this hydrogen is 1 degree hydrogen or primary hydrogens. In the other side, you see this in this hydrogens, this hydrogen attached with this carbon, and this carbon is also attached with the another two carbon. So that's why this is called the secondary hydrogen or 2 degree, and thus the 3 degree we called also the tertiary hydrogen. Now the conformation. Conformations are different arrangement of atoms. So you see the different arrangement of atoms that are intercorporated by rotation about single bond. So you know that in the alkane there is a single bond between carbon and carbon. If you rotate there is a fixed angle. If you rotate, we can change the different arrangement of the atoms. So we call this conformation. A particular conformation is called a conformer. So you see that in this picture the carbon single bond here. So if you rotate this, the conformation is changed. So there is a two different conformation. So this when the two different conformation is, one is eclipsed conformation, the other is staggered conformations. In the eclipse conformation, we see that the carbon hydrogen bonds on one carbon are directly aligned with this is the carbon and directly aligned with the other carbon, aligned with the carbon hydrogen bonds on the adjacent carbons. You see that this is the carbon bond, and this is the carbon hydrogen bond, and this is the carbon hydrogen bonds is aligned with the same way. But in the staggered conformation, we see this is the carbon, but we see this is the carbon hydrogen bond, this is the carbon hydrogen aligned with the different so in the staggered conformation, carbon hydrogen bond one carbon bisect hydrogen bond angle on the adjacent carbon. So there is an angle between this this angle is equal to 60. So if you rotate the eclipse conformation 60 degree about the single bond, this will form the staggered conformations, and the vice versa. So if we see that in the eclipse conformations, in the carbon carbon is aligned with the same way, that's why the dihedral angle is 0 degree. So what is dihedral angle? The angle that separates a bond, the angle that separates a bond, one atom from a bond on an adjacent atom, is called dihedral angle. So here you see that the carbon carbon is aligned with the same way, that's why the angle separate bond one atom to another atoms is 0 degree. That's why the dihedral angle is 0 degree in the eclipse conformations. But if you rotate one carbon with respect to the another about 60 degree angle, this will form the staggered conformations. So that's why in the staggered conformation we see that the hydrogen carbon hydrogen bond is 60 degree. This is the dihedral angle. So here you see that in the staggered conformation the dihedral angle is 60 degree. So compounds, we see that they are three-dimensional, but we are limited to two-dimensional sheet of paper when we show their structure. So that's why there are three methods of represent on paper the three-dimensional arrangement of atoms that results from rotation about the bond. These are perspective formulas, Sohor's projection, and the Newman projections. So we see that in this picture there is three different way to show the three-dimensional hydrocarbons or alkanes. So in these perspective formulas we see that the carbon carbon hydrogen is the plane in the paper, and here you see that there is a dash line, hash line, and there is also a dash line. The hash line means the carbon hydrogen, this carbon hydrogen bonds is into the paper, and this carbon hydrogen bonds out from the paper. So the carbon carbon hydrogen is on the paper, and the carbon hydrogen bonds is the hash line is represent the into the paper, and the solid line and the fill up line, that means this line is represent the out from the paper, and the solid line is represent the on the plane of the paper. So in these perspective formulas, here you see that solid lines are used to for bonds that lie in the plane of the paper, solid wedges for bonds represent out from the plane of the paper, and has wedges to bonds extending behind the paper, that means into the paper. So that's why we can represent the three-dimensional structure of alkane by the perspective formulas. And then I have to see that the Sears projections, and the Sears projections, there we see that the carbon carbon bond, this is the carbon, this is the carbon carbon bond. So this is the carbon carbon bond, and this is the first carbon, this is the second carbon. Here you see that there is the all bond in the plane on the paper. The hydrogen carbon hydrogen bond is also shown in the source projections. In the Newman projections, we see that there is a circle which represent the carbon. So there is the two carbon. So in the Newman projections, the carbon is found is represented by the point at which the bonds intersects. So this is the first carbon, and this is the first carbon. The three bonds of intersect the carbon hydrogen bond. This is the carbon hydrogen bond. This is the carbon hydrogen bond, and the other carbon is that the circle represent the other carbon. So the other carbon has also three carbon hydrogen bond. Here is present. This is the eclipsed form. Sorry, this is the staggered conformation, and this is the eclipse conformation. Okay, so that's why there is a three types of represent the alkane in three-dimensional structure on the plane or the paper. Okay, so here we see that in the we consider about the staggered conformation and eclipse conformations. The staggered and eclipse conformation of ethane interconvert at room temperature, but each conformer is not equally stable. So we can convert staggered to eclipsed or eclipsed to a staggered by rotating about 60 degree angle about the carbon single bonds. But each conformer is not equally stable. That means the staggered and eclipse are not equally stable. Because of what? Because of that, the staggered conformation are more stable, lower in energy than eclipse conformation. What? uh, so here we see that by this line we see that the staggered conformation are more stable. So what is the reason behind the more stability? The reason behind the more stability is in the staggered conformation we see that their electron repulsion between bonds is less. You see that in the staggered conformation the electron conformation is less than the eclipse conformations. So that's why the electron repulsion between bonds in the eclipse conformation increases in energy compared to the staggered conformations, while the bonding electrons are further apart. Because in the staggered conformations the bonding electron is further apart. That's why the electron repulsion is less, so energy is less. But in eclipse conformations energy less, but in eclipse conformation carbon hydrogen bonds are closer together, rather respective to the staggered conformations. So that's why the electron repulsion is high. So you know that if there is a lower in energy, this will be more stable. If the higher in energy, this will be less unstable. So that's why the staggered conformation is more stable than the eclipse conformations. So it is very important things. So what is the difference between the energy? So the difference between the energy between staggered and eclipse conformations is about 2 3 kilocalorie per mole. So with each eclipse carbon hydrogen bond contributing 1 kilocalorie per mole, because here we see that the carbon hydrogen bonds is three bonds in carbon hydrogen, so each of the carbon hydrogen bond contributing 1 kilocalorie per mole, and the total, that's why the total um, energy in the conformance is equal to 3 kilocalorie per mole. So here is the difference between the energy between the staggered and eclipse conformation is called torsional energy. This is the important things. So what is torsional energy? That the energy difference between the staggered and eclipse conformations is called the torsional energy. It is about to the 3 kilocalorie per mole. So the torsional strain is an increase as is energy caused by eclipse in interaction. So in this we also see that in eclipse conformations the energy is high rather than the staggered conformation. So here you see that in the graph there is a y-axis in energy and the x-axis is trihedral angle. So here you see that the eclipse energy is maximum and the staggered energy is minimum, and the difference between the energy is 3 kilocalorie per mole. Now we can analysis conformation analysis of butane. So here you see that if we consider rotation about here is the bond of butane, carbon bond of butane, and there is a 6 important conformers. So here you see that this is the one, an conformation. So this is the Newman projection process of the represent of 3D alkane here use. So in first structure here you see that, and this is the first one carbon, and this has one carbon hydrogen bond. This is the one carbon hydrogen bond. This is the carbon CH3 bond, and the another carbon is that the circle, and this also have the same bonding, but here you see that the methyl group is the opposite to the others. Okay, so that's why it is called the anti-conformation. But in see that the eclipse conformation they align in the same way. Here you see that in the eclipse conformations aligned with the same way, carbon hydrogen bond, the two different carbon. Okay, so in the another form these three, the Gauche conformations. In Gauche conformation here you see that the methyl groups is beside one and another, and also the in eclipse conformations the 4 and 5 is also a Gauche conformations, the carbon methyl group beside each other, and the eclipse conformations here you see that. So there is the 6 different configurations, and anti-conformation, eclipse conformation, and Gauche conformations. Here you see that. Okay, so in this we see that the anti-conformation does not have torsional strain from steric hindrance because the groups are staggered and the methyl groups are far apart. Anti-conformation, the methyl group is opposite to each other, so that's why there is doesn't have any torsional strain. The anti-conformation is the most stable because there is a further, so electron diffusion is less. That's why the energy is less, so that's why it is more stable. The methyl groups in the Gaussian conformations 3 and 4 structure are close enough to each other that the dispersion forces between them are repulsive. The electron clouds of the two groups are so close that they repel each other, so the repulsion causes the Gaussian conformations to have approximately 3.8 kJ per mole more energy than their anti-conformations. In the eclipse conformation 2, 4 and 6 represent energy maxima. In the potential diagram, eclipse conformation 2 and 4 2 and 6 have repulsive dispersion forces arising the eclipsed methyl groups and hydrogen atoms. Eclipse conformations 4 has the greatest energy of all because the added large repulsive dispersion forces between the eclipsed methyl groups are compared to 2 and 4. So if you see in the graph, so it will be more clear for us. Here you see that in the graph there is y-axis in the potential energy, in this x-axis the rotation about the single bonds. So here you see that if you have 0 degree rotation, that means the anti-conformations, which is the first exertion of our experimental consideration. So in this first consideration we see this the anti-conformation. Here we see that the carbon methyl group is opposite to each other, so that's why the electron diffusion between each others is less, that's why the energy is less. So here you see that this for energy is less. And then if we rotate this 60-degree angle, this will form the two configuration, eclipse 2 form, which is eclipse formation. So here you see that the carbon is aligned with the same way, and this energy will be increased, and then the anti-conformations, which is 16 kilojoule per mole. If we rotate further 120 degree, further 60 degree, that means total 120 degree, this will form the Gaussian conformations. In the Gaussian conformation, you see that the carbon methyl is beside each other, but it is in the staggered configuration, so that's why the energy is less than the eclipse conformations. So this is the less energy. Where you see that this is the less energy. Okay, if you rotate further 60 degree, it will form eclipse 4, but in this form we see that the methyl group is beside each other in the same way direction, so that's why the electron diffusion will be high. That's why the energy is also high, which is the maximum energy in this experiment of our considerations, which is 19 kilojoule per mole. Okay, so if you further rotate 60 degree, this will form the Gaussian 5 configurations. Here you see that this formation and this formation is almost same, so that's why the energy is same with each other. The Gaussian 3 and Gaussian 5 confirmations is the same energy. Okay, and then if we rotate the 60 degree further, this is from the eclipse 6, which has, we see that this is the same as the eclipse 2. Eclipse 4 is same as eclipse 2, that's the same energy. And if we further rotate 60 degree, this is from the anti-conformations, which is same with the first configuration. So that's why we see that the first and 6 confirmation are same, and 2 and 4 confirmation are same. 2 and 6 confirmation are same. That means 1 and 7 is same, 2 and 6 is same, 3 and 5 is same, so 4 is different. And the energy between the 1 and 3 is 3.8 kilojoule per mole, because here you see that in this one the methyl group is larger further than the Gaussian conformations. In the conformations of 3 structures, here you see that the methyl is conformation beside each other, so that's why the energy in the 3 or Gaussian conformation is higher than the anti-conformations, which is 3.8 kilojoule per mole. So that's it.